Yes, hello. Thank you for giving me the opportunity to speak today. I'm going to talk about very simple chemistry and about the abiotic formation of methane and coupled to the serpentinization reaction happening on olivine grains and the carbon dioxide, how it's affecting these reactions. So the aim is just to investigate any possible formation of methane at these low temperature serpentinization reaction and to see whether or not CO2 is inhibiting or enhancing this reaction. So to do this, we have performed a series of experiments, very simple experiments in which we have mixed natural forest-deritic olivine sand with either pure water solution or a weak bicarbonate solution or a stronger bicarbonate solution. And we have mixed it in these incubation bottles that you can see over there. And then we incubated these bottles for 315 days at 3 different temperatures, 30, 50, and 70 degrees. And we had a pressure of 1 atmosphere, and the pH was around 7 to 8. And we have flushed the bottles, the headspace of the bottles with pure nitrogen in order to get it totally anaerobic. And the reason why we are using olivine is because when olivine is exposed to liquid water, it may form hydrogen according to this serpentinization reaction, in which olivine and water is forming serpentine minerals, brucite minerals, and magnetite and some hydrogen. And the actual reaction that is happening is that iron 2, the reduced iron 2 plus is getting oxidized into iron 3 plus, and at the same time water is reduced into hydrogen. And this hydrogen can be used again to reduce, carbon dioxide into methane. And since olivine is abundant on Earth and in space, especially on Mars, whenever you have carbon dioxide and water together, you may form methane. And we wanted to investigate the low temperature and low pressure conditions and to see whether or not it's possible at all to produce this methane at these low temperature regions, because many studies have been performed earlier in a similar way, but they have used very high pressures and very high temperatures. And so what we could see after incubation of almost 1 year is that the hydrogen formation rates are higher in the low bicarbonate buffer solutions, and in the high, strong bicarbonate solutions, it's very low hydrogen formation rates. And in between, we have the pure water. And we can also see here that in the 30-degree experiments, you have very large error bars, and the system is very unstable and out of equilibrium. And you can also see that there is an increase of hydrogen formation rate with an increased temperature. And you can see the similar pattern in the formation of methane in these bottles. Here you can see 30 degrees and 50 degrees and 70 degrees experiments. And you can also see in the 30 degrees experiment that the error bars are very, very large. So it's a fluctuating non-equilibrium system. But it's also very interesting that you can see that the same pattern is happening, that the the weak bicarbonate solution is producing more methane than the water, and also that the strong bicarbonate solution is inhibiting the formation of methane. And we believe that the reason why we see this pattern is because if you compare the water and the weak bicarbonate solutions, you are decreasing the pH in the weak bicarbonate solution, and that's why you're increasing the kinetics and producing more hydrogen and thus also more methane. But when you increase the bicarbonate concentration too much, you get a precipitation of carbonates instead. And if you precipitate carbonates, they will incorporate the iron 2+ into the crystal structure, and thus it will not get oxidized into iron 3+, and then we will not have any hydrogen to reduce carbon dioxide. And that's actually also what we saw in our experimental bottles. After 1 or 2 months, precipitates were starting to appear in the strong bicarbonate solution experiments. And when we analyzed these precipitates, they contained amorphous silica, some amorphous silica, carbonates, magnesium, and a lot of iron 2+, so the reduced iron, which supports the idea that the iron 2+ is incorporated and cannot react with carbon dioxide. And if we compare our results with the earlier results, we can see that we have a very, very low yield of methane in solution compared with other studies at higher temperatures and higher pressures. And that's mainly what we think is mainly because of the very low temperature and also maybe the higher pH. So the summary here is that we have a possible formation of methane in water and in a weak bicarbonate solution, but it's a very, very slow process. And we see almost a total inhibition of methane formation in the strong bicarbonate solution, and that's mainly because of the iron 2+ incorporation into carbonate precipitates. And we have to do a lot more studies to see the coupling between the precipitates and the metals and other catalysts and pH, etc. We have not included any catalysts, for example, in our studies. And many of the other studies that have been made by strong catalysts. And I also want to say that it seems that the hydrogen that we have formed in our bottle seems to be enough to sustain the growth of hydrogen-trophic archaea and olivine together. And we have a poster, my colleague Duck, and I have a poster that I recommend you to look at. Okay, thank you very much.